Hello and welcome to Chemspec Digital 2021. I have the pleasure to introduce the next presentation in the RSC Lecture Theatre. However, before I do, I would like to point out that our sessions are being recorded and will be made available to view on demand on the platform later on. Attendees are invited to write questions to the presentations in the chat function on your screen, and we will read them out at the end after the presentation. But for now, without further ado, I will hand over to both our speakers, Anna Carden and Dr. Jordi Ampodanes, who will be presenting Go Flow Under Pressure.
Thanks a lot, Christiane, for this nice introduction. And yes, I'll talk about our flow reactors and ethoxylation in those reactors. So we will start with a short introduction. This will be my part, how to go from batch to continuous. I will introduce you to the microbial technology and explain a bit our scale-up principle from lab up to production. After that, I'll hand over to Dr. Jordi Ampodanes, and he will come to the more exciting part. He will show some real examples which we did run on the lab, and talk about automation possibilities and, of course, the production example. So let's start with my part. What do we do? So it is like a paradigm shift you have to do from batch to continuous flow. And if you're now working in flow, there's some things you have to think about when you want to translate your reaction from batch to continuous. First of all, our reactors normally have the operating conditions with temperatures up to 200 degrees, pressures up to 100 bar, and we use stainless steel or alloy because they are really good in transferring heat. So either heating up or also cooling down. Of course, there might be some corrosion problems here, so this is why we, on top to stainless steel, offer also the alloy version. So how to do it? So you see here a flow schematic. We have the two tanks, we have pumps, we have a mixer, a residence time reactor, and our product. So what we do, or what we can change, there are several variables we can work on to optimize our reaction in continuous. That's, for example, the concentration. So we can change the concentration. That's one variable. We also can change the flow rates with pumps, and we have the possibility to change pressures and temperatures. And this hopefully will lead us to optimize product in the end. So we work on, like also our name does say, it's Ethoxylation microtechnique, but the first important thing is that we are not longer working really in microstructures. So we use millistructured channels because if you want to do a scale up from lab up to reproduction scale, then you can't use these really small microchannels. They're so easy to block, and also you can't go to this high flow rates and throughput. So we use millistructured channels. But we remain the benefits. So we have the rapid mixing, of course, we have the rapid heat exchange, and we have a well-defined residence time because we can measure all the structures in the reactors. And because of the small hold-up, we have a real short response and reaction time. So that's always like one of the first questions our customers ask. So how to do it, how or which reactions make sense, where to go from batch to continuous. So that's normally the first really interesting question. We have here an overview about attractive market segments, and what you can see in the explanation for these reactions, it's always about fast reactions. We have high exothermic reactions, we can handle explosive reactions. So we made like a short assumption of the market segments, and interesting are active ingredients, precipitation, peroxide, and ethoxylation and sulfonation. So these are for us the attractive market segments, but of course there are a lot of others. But in this presentation, anyway, we'll focus a bit on this reaction type, on ethoxylation. So what do? We have two different concepts. We have plate heat exchangers. There are two of them. We have the long-style flow plate reactor and the arc plate reactor. So these are really these well-known plate reactors. We have a one-channel structure, and we do the scale-up with widening the channels and lowering the channels. So in this presentation, we will focus on a tube bundle heat exchanger. So it's an analogy to a tube bundle heat exchanger. We call this our Myprova reactors. Here we don't have a one channel structure, we have several channels. I'm not sure how good it is to see here, but you can see a lot of rectangular small channels in this overview, like in this small square. So I'll show you the channels a bit closer. So this is one of these rectangular channels. You can also see here the lab version we have. This is called our Myprova lab. It fits in a fume hood. It's just 30 centimeters long, and we have these rectangular channels. So why rectangular channels? Normally everybody's used to the round channels, but with this rectangular channel, we already have most of the fluid on the wall. So for the heat exchange and the higher surface volume ratio, we choose this geometry. And of course, we have a laminar flow in the channel. And as you can easily see on this picture, the fluid in the middle would never contact the walls. So, but this is what we want to have for the heat exchange. So we want the fluid to contact the wall. This is why we use these mixing structures. So you can see the small yellow arrows. With these mixing structures, we can interrupt the laminar flow, we can create turbulences, but that's important, we never get chaotic. So we can prove by the Reynolds numbers that we stay laminar, we just create some turbulences for better mixing, and of course for better heat exchange, because all of the molecules in the fluid will somehow contact the wall. So that's the important thing about these mixing inserts. So how do we do the scale up? As mentioned, in the lab, we have this 30 centimeter Myprova lab. And for the pilot scale, we do a bit of widening the channels. You can see that here. So we go from 12 to 1.5 to 18 to 3.2 millimeter. So we widen a bit the channel. Yes, this means we lose a bit of this heat transfer capacity, but the small reactor is a bit overdoing, so it's one of the best heat exchangers you can imagine, and even if you lose a bit of this heat transfer capacity, until now it didn't matter. So also working with peroxides or something like really exothermic reactions, it was still so good that the heat exchange was more than enough. So we have the small step, lab to pilot, and when we have our pilot scale reactor, this is also a reactor which you can handle in a fume hood, so it's not that big, it's 1.20 meters long, and we make our long test runs in this pilot reactor. So this means we use the real chemicals, we try to do like what's really happening later on in the production at the company. So if we did this pilot scale, of course, now we are going to the production scale. So we design a production reactor with the results we have here from this pilot scale test. So with the pilot scale, with the production reactor, we use the same channels, so same geometry, same channel size, but we number up the channels. So it's just several channels in a row. And in this case, we just put one core. So imagine this is one reactor core. So we can add another core and another core and another core to a certain length. So and this is how we can make sure that the customer gets the right throughput he wants to have for production with the right residence time. So yeah, this is what we already saw. This is one of the cores, so here it's open. Normally there's an end flange, but here's the open version, and you can see the small rectangular channels. Here we have an overview. So as mentioned, we have the Microba lab, the pilot scale we call matrix, and then we have the Microba production reactor. So here it is interesting that we keep the same channel size. Again, what happens in the lab, in pilot, will also happen in the production reactor. So this makes the scale up so easy and fast. And we have here up to several cubic meters of throughput in such a big reactor. But anyway, Jordi will come to a project talking about this technology later. So here I have an overview to show you again this rectangular channels and why it's so important to use these mixing inserts. Here we have the K value, and here we have the product mass flow. And in gray, this gray line is an empty channel. So it's an empty channel in the Microba matrix. And as you can see, it's already a high K value. So we have above 1000. But if you use these mixing structures, so you can see here all the lines with the different mixing structures, you can see how much better the heat transfer gets. So here we are really above 2000, so we doubled the K value, so the heat exchange capacity is doubled with the mixing inserts. Also a nice add-on is that we have these mixing inserts in different shapes. So here on the right side, you can see the different shapes, and here we can change the flow velocity. It's also depending on viscosities, and you really can choose according to your chemistry the right shape of these mixing structures. Yes, I think that's the short introduction into the Microba technology. So yes, now it's a pleasure for me to hand over to Dr. Jordi Ampordanes, and he will tell you a bit more about really using these reactors. Jordi, your turn.
Okay, Anne, thank you very much. I'm going to share my screen. Yes, very good. So first of all, good afternoon, everyone. Yes, so as my colleague Anne said, my name is Dr. Jordi Ampordanes, and I work for Erfeld Microtechniek as a process chemist and engineer in our laboratories. In the next slides, I'm going to talk about ethoxylation using our Microba reactors technology, and also the implementation of automation for a better and safe control of the process. So, yes, very good. So just in short about what ethoxylation means, is simply the addition of ethylene oxide into a substrate, which in the end would lead to the formation of a product and also the release of heat. Sorry. Yeah, so heat release, so which means that is an exothermic reaction. And then important parameters to take into account when one wants to run this type of reaction are the following ones. Yes, so which make this process a bit tricky to really handle in a regular condition. So ethylene oxide is highly flammable and toxic. Mixtures with air are highly explosive in a range from 2.6 up to 100% in volume. There is a limited stability of the reactant and the products. And finally, as I said before, it's a highly exothermic process, so there is a heat release. Then it makes all these parameters make this process difficult to handle in batch conditions. Especially because we are talking about large volume of reactors, several reactors, in fact, operating at the same time, long reaction times, and since it's an exothermic, highly exothermic reaction, you can imagine the amount of heat that is released. And yeah, also there is the formation of side products and also the capacity in this case. Just, yeah, I think something, yeah, very good. Capacity, the capacity is limited in this case then. Our approach, the way that we think or that we have to approach to this ethoxylation in continuous flow is to make use of the MyProva technology, MyProva reactor technology, which has the rectangular channels, which provide high surface to volume ratio. And these rectangular channels are combined with mixing inserts. These mixing inserts will allow, which as you can see here, and as my colleague Anne said before, will allow the fluids going inside to really move in all directions, and in this way to enhance the heat transfer, as well as the mass transfer and narrow the residence time. So in a way, trying to achieve kind of plug flow behavior. Yeah. In this next slide, what I'm showing here is a picture taken in our laboratories where we are showing the setup for ethoxylation using MyProva Lab, the smallest reactor of the MyProva family. In this case, this is a demo or a demo system, because most of the times when we run ethoxylation projects, we do it at client side. Then what we have here, we have first of all, this is the MMRS setup, including the MyProva reactor, which is this one. Here we have heat exchangers, back pressure regulators, and sensors. On the right-hand side, we have the automation unit. In this case, for us, automation unit means the hardware, which is this so-called lab manager supplied by High-Tech Zhang, but also, so not only the hardware part, but also the software part, which is the lab vision. So in order to have a complete automation unit, one must make use of both the hardware part and software part. As you can see here, there are several connectors on the automation unit where pumps, thermostats, all kind of peripherals plus sensors can be connected. And yeah, then back to the setup for continuous ethoxylation. Here we have the peripherals. In this case, we would be talking about pumps, mass flow controllers, and thermostats in most of the cases. Also, one can go one step beyond and make use of a dosing system, dosing unit, which already has incorporated or integrated the mass flow controller or mass flow meter, plus the pumps, plus several valves, plus some pressure indicators. So this would be an all-in-one. So now I would like to move. So this was regarding how the setup looks like to run an continuous ethoxylation in continuous flow in laboratory scale. Now I would like to present or talk a little bit about what are the benefits of the automation for such kind of projects. So first of all, I would like to say that automation, looks like it helps to really combine. So flow chemistry and automation can be combined for continuous flow processes. And in this way, for example, a setup like one might have in the laboratories for a continuous process, like this one I'm showing here, can be fully automated, meaning that, for example, we would have pumps. These pumps require a certain flow rate, or certain flow rate has to be defined, and also for example, the volume of the reagents that has been spent can be calculated. Then we would go from pumps to a mixer, and from the mixer to a continuous reactor. In this reactor, it's interesting to follow temperature and pressure, and at the outlet of the reactor, it's also interesting to evaluate the quality of the final product. Quality meaning, for example, the yield, final concentration, and similar things. This can be done by means of optical or spectrometric measurements. And also interesting to measure is the amount of product that has been formed, so the kilogram of final product. So all these things can be done by means of automation, and they can be really easily implemented in order to have a very easy to handle setup, which in turn would allow to really run plenty of experiments with minimum effort, because everything could be automatically controlled, and just simply it would be only a matter of defining parameters, reaction parameters. I'm going to move to the next slide. Yes, so here what I'm showing is a scheme of how we would approach our the continuous ethoxylation. So this is just as I said, a drawing, and here in black, what you would see is the equipment that we would carry with us to a client's site in order to conduct proof of concept. But in this case, we do not only carry with us reactors, but also pumps and thermostats. And in this way, this can be integrated in the infrastructures that the client provides. As I said, we would bring reactors, thermostats, pumps, and so on. So in blue, we would have like the infrastructure part, or like the part of the project that the client would take care of. Yeah. Since ethoxylation is ethoxylation is very crucial to take much care about EO, because EO is very hazardous. For this reason, the safety concept has to be integrated at client side. And just to show you how we approach to this, in the next slide. In the next slide, I'm showing a graphical representation of a project that we set up for ethoxylation some time ago. The setup in general may not seem that complex, but in terms of automation and process control is one of the most complex projects that we had so far. As I said, because due to the presence of EO, many safety measures must be applied in order to avoid any problem. Yeah, so here we have the MyProva reactor, MyProva lab reactor, here an additional reactor for additional residence time. We would also have heat exchangers, pressure sensors, also some temperature sensors also here throughout the reactor. And we would also have the pumps, mass flow controllers, and so on. And then what we have here, for example, is the feedstock dosing line going to the reactor. Here we have the EO feed line. In this case, in case of EO, it's usually controlled by a pneumatically driven valve, since it is crucial to prevent EO to react in the event of something unexpected. So with this automation implemented in this setup, it's not possible that there is flow of EO if there is no flow of feedstock, and at the same time, if the reaction conditions are not met. No? So this is an important contribution of the automation. Some other contributions coming from the automation are, for example, the perfect control of the flow rates, as I said before, the possibility of setting the right reaction temperature through the thermostats, control the filling level, for example, of the feedstock vessel in this case. So always knowing what's the amount of feedstock left, because as I said before, it's always important that EO is not reacting if there is no flow of EO of feedstock. And and then also there are some additional safety trips, pressure shutdown, overall shutdown, which like by clicking some buttons, this happens. Then that was what I've shown before. That was really regarding the what automation can do to improve the ethoxylation in continuous flow. Now what I want to show briefly is like how we move from lab scale to production scale. My colleague Anne already said several words about this, so this won't take much time. So in this case, we have started, or we would have started from the MyProva lab. We would move to MyProva matrix in this case, where the increase on the geometrical dimensions of the rectangular channels would change. And then from this size of channel in MyProva matrix, we would move to the final production reactor. And so it's only mattering in this case when we are in the validation phase, just to make a numbering up of channels. I would also like to say that in case of the validation phase, it's also possible to apply, so to make use of the automation to control the process properly. And once we move from validation to production, the reactor is completely designed. And then here, what I'm showing is again the slide, one of the first slides that I've showed when I started my talk, my presentation here, like talking about the ethoxylation using batch reactors. So as you could remember, so very large volumes, several numbers of reactors were used, the batch time higher than 100 hours, formation of side products and so on. So then now what I'm showing is the real example of what we did with one of our clients. So this is a reactor, production reactor that we have installed in China for, our clients are Chinese. They are called Shaoxing East Lake High Tech. They are located close to Shanghai. And after doing following all the seamless scale-up process, we end up with one single reactor with a capacity of up to 10,000 tons per year, with a volume of only 40 liters, which is more or less 1,300 times less volume as the one we have for batch reactors, with a residence time of 3 minutes and an increase of yield of 15%. And also interesting to say is that this production reactor was commissioned in China in just 1 week, with the final product already meeting the specifications. So as you can see, the process was quite fast when moved from lab to validation to production. It was the timeline was not that long, let's say. And last slide, I would also like to say to highlight that, as you can see here, also the capacity was increased by a factor of 3. So in batch, we were talking about 3,000 tons per year, and with one single reactor, 10,000 tons per year. And finally, this is my last slide, and with this picture, I would like to finalize my presentation. This is a real picture of this MyProva production reactors installed in our client site in Shanghai. So for the moment, they have 3 reactors, and they are like 7.2 meter long. So this is how they look like. And just would like to say that thank you very much for your kind attention, and my colleague Anne and myself are looking forward for questions to come and to kindly try to answer them. Thank you very much.
Brilliant. Thank you very much to both of you. Now, this does bring us to the question and answer section of the presentation. If there are still some questions out there that you would like to ask our presenters, please feel free to still put it into the chat box. There's a couple that have come in. So what's the typical timeline for a change from batch to continuous?
Yeah, I can
Anna, please.
So yes, it is pretty different, to be honest. So normally we have this translation batch to continuous, and it's a bit depending on the reaction itself. So the reactions which handle just the simple mixing of two fluids, there the transition is pretty easy, but of course we also have in APIs, for example, there's several step reactions, so up to 7, 8, 9, 10 different ingredients needs to be mixed, and then of course it takes a bit longer. But normally we would say, like what George is also doing, this feasibility study, so the first trial is normally 1 to 2 weeks, and then we have an idea where the benefits are, then we can optimize. That might take another 3 to 4 weeks to do real optimization to the end. And afterwards, we do this pilot scale trials that might take up to a month. And after that, normally we sit down and we design the production reactor. So from lab up to production, maybe something, yeah, to 6 months in total. Always depending on the availability of Jordi and his colleagues.
Yeah, that's a good point. Yes.
Right now.
Well, yeah, absolutely. Thank you for that. That's good. The other question that was coming is, how do you choose the right reactions for continuous flow? So,
shall I answer, Anna? What do you think?
If you like to.
Okay, so let's do half of the job. So, yeah, in this case, for reactions to be implemented or to be really used using our equipment, we are mainly looking for fast reactions, highly exothermic reactions, also hazardous reactions, which in principle, they are too dangerous to be really done in batch reactors, which, yeah, they are difficult to be done in batch reactors, but in continuous, like the risks are less because of less volume and easy to handle, for example, or easy to remove heat if there is heat release. And yes, so basically that would be the 3 main type of reactions. However, this doesn't mean that we are not open to really discuss for all kinds of reactions with our clients. So we are here to really listen to our clients' needs and try to find the best solution or the best approach to tackle their, what they want to do, basically.
You should go into what challenges they're facing in order to move to continuous. Okay. Yeah. Excellent. Well, thank you so much to both of you for presenting today. And we do invite the audience to reach out to FF Mikrotechnik, to both Jordi and Anna on the platform. There's still time to arrange meetings with them or to another member of their team. And we thank you all for attending and for watching, and a special thank you to presenters, and we wish you a great afternoon. Thank you. Bye-bye.
Thanks a lot.
Thank you.
For you too. Bye.
Bye-bye. Have a nice day.